everybody and welcome to this workshop at the Things conference. Unfortunately, we are not able to meet in person this time, but anyway, it's great to have the opportunity to join this conference again in a virtual way. I'm Itziar de la Torre from IMST, working at the Wireless Solution Department, and here I will give you an overview about LoRa on the 2.4 GHz frequency band. Let's start with it. This workshop introduced the features and capabilities of LoRa on 2.4 GHz and provides you a basic understanding to start developing your own system. This is supported by your new family of products that allows you to reduce time to market. At the end, you will see a demo showing how to build your own application on an end device using a temperature and humidity sensor, and how to connect it to the Things stack and visualize the sensor data in the TowerView platform. As other sessions at the conference have already covered the basics of LoRa, I will not go in details at this point. Just as a brief introduction, LoRa consists of a proprietary modulation owned by Semtech and based on the chirp spread spectrum. This has been especially designed for long-range applications, offering at the same time low power consumption. Currently, this is already in use in many applications within the unlicensed ISM band using the sub-gigahertz frequency range. For example, in Europe, such applications are often realized in the frequency band at 433 or 868 MHz. The reason for this is that these low frequencies are subject to less propagation losses, and therefore this allows a higher communication range. On the other side, there are two disadvantages that affect those frequency bands. First, that these frequencies are not harmonized worldwide. And second, the duty cycle that has to be fulfilled in some regions. Besides, 2.4 GHz is a worldwide harmonized and unlicensed frequency band. And therefore, the main advantage of using it is that it simplifies the required radio approval process. Despite the fact that 2.4 GHz is a cloudy band, the robustness of LoRa, with a really good link budget of more than 140 dB, allows a range of even 10 km in a line-of-sight environment. Additionally, using this frequency provides the benefit that there is no duty cycle restrictions if the device limits its power to 10 mV. If you decide to start your application or product with 2.4 GHz, IMST has already updated its portfolio. Similar to the products available for LoRa in the sub-gigahertz frequency band, we offer a radio module and a multi-channel concentrator which can be integrated into a LoRa gateway. Our radio module to be used with LoRa on 2.4 GHz is named IM282A. It contains a contact entry with a Semtech transceiver, and this has been especially designed for battery-driven applications and does not require any additional amplifier. And to simplify its integration in your product, this is pin-to-pin compatible with our other radio modules. We also offer a multi-channel concentrator for this frequency, named IC288. This is a mini PCI Express card which contains 4 Semtech transceivers. One of them is used to transmit the messages, while the other 3 allow the reception of messages using 3 different radio configurations. Additionally, we have a new version of our LoRa gateway which can be used for 2.4 GHz. This consists mainly of a Raspberry Pi 4 and our new concentrator, everything built into an aluminum housing. This is meant to be used as demonstration system with the LoRa network, and it's designed to be used in an indoor environment. Finally, if you would like to try LoRa on 2.4 GHz, we provide 2 kinds of LoRa development tools to start with. These are our Wymodino board and our starter kit. Both of them will be present here later on. On the end device side, we offer different software solutions. Our LR-based Plus software allows a device-to-device communication. This includes several features such as the exchange of confirmed and unconfirmed radio messages, including an optional encryption algorithm, automatic power saving for battery-driven applications, and a communication through the serial interface to control and configure it by an external host. This includes also an additional feature, which is a radio link test to analyze the radio link quality using different radio parameters. This can be really helpful during the feasibility phase of your project. And this can be easily started using our starter kit and studio. As a preparation, both devices should be configured with the same radio settings and as continuously listening. Then, this test application can be started and it measures the packet error rate by counting the number of transmit and receive packets on the local connected device and the peer device. Then you could see how these parameters change with the distance of both devices. For this example, to simulate the increment on the distance between both modules, we have removed the antenna on the peer device. That explains why some packets are missed and the packet error rate value starts increasing. After connecting the antenna again, the packets are received and the packet error rate decreases over the time. This application could help you to verify and check if the range of LoRa is adequate for your system. On the other side, if you would like to build a system emulating a LoRaWAN network, you could choose between two options. Our radio module is compatible with the Semtech LoRa 2.4 GHz stack, which is available as open source code in GitHub, and allows you to create your own application directly on the microcontroller. Another option is to use our Global Link 24 software, which provides a communication through the serial interface to control and configure it by an external host. In this case, our studio allows you to configure easily your device. For example, you could set a device UI, and for this you have to set the operation mode to custom mode previously. You could modify the radio configuration parameters and customize your device with the activation keys and activate it. Now is the device ready and it's possible to connect it to your network server, for example the Things stack, and you could visualize the radio message exchange. This includes the complete activation process and the application data and downlink sent afterwards. Now you know everything you need to start creating your own application. At this point, I will guide you through a quick demo. If you would like to repeat it by yourself, all you need is one of our LoRa gateways and an end device based on our Quai-Motino and a temperature sensor. And of course, don't forget your registration at the Things stack. I will use our Quai-Motino to build an end device. This is our development platform compatible with Arduino, and it supports our different radio modules. Its main advantage is that it could be used for fast prototyping, as a huge number of libraries are already available. In this demo, the Quai-Motino includes our IM282A device for 2.4 GHz, which is programmed with our Global Link 24 software. With this, the example application will run directly in the Arduino controller, and this one will configure and control the radio module through the serial interface. To complete the integration of the end device, a temperature and humidity sensor will be connected using the I2C interface. and for this an extension board will be used. During this demo, we will emulate the LoRaWAN system, which is based on three main components: an end device, a gateway, and a server, where the main role of the gateway is to forward the messages exchanged between the end devices and the server. Basically, the end device can be classified in three different classes. These are Class A, where after each transmission of the end device, two receive windows are opened to allow a possible downlink from the server. A Class B device is compatible with Class A with additional receive windows controlled by beacons sent by the network. And a Class C device is also compatible with Class A, where the end device is configured as continuously listening as often as possible. Here, we will configure our device as Class A. Before a communication between the end device and the server can be started, the end device needs to be activated. For this, there are two options: activation by personalization or over-the-air. In this example, the over-the-air activation will be used. And after a successful activation, the end device will be configured with an address and a network and an application session key. Now the end device is ready for a secure communication with the network server. And in this case, our end device will send the sensor data to the Things stack. Our light gateway provides a simple way to get it up and running, as this includes the GitHub repository developed by Semtech pre-installed. Basically, everything you need is to power it up and connect it to your computer with an Ethernet cable to gain access to it via SSA for its first configuration. After a power-up, a service that starts the packet forwarder will be automatically running. Therefore, you could start stopping this service. And after doing this, the LED that shows the status of this service will turn red. It could be also helpful for you to know the chip ID of this concentrator. And for this, you could run the corresponding application included in the GitHub repository. Then you will need to modify the parameters in the global config file according to your application. This works in a similar way as the current packet forwarder for the sub-GHz frequency band. Here, you could configure if your network will be used as public or private. And you could specify the three different direct channels, including the frequency, bandwidth, and the spreading factor for each one. You could also customize the gateway ID or just set it to auto if you want to use the chip ID of the concentrator instead. Finally, you should enter the corresponding server address and port, and in this case the Things stack will be used. Now, if you start the packet forwarder manually, you will see in the screen the debug information. As the gateway ID is set to auto, the chip ID will be used for this. In addition, all the information related to the radio messages will be shown. Let's continue with the system setup in the Things stack. Here, you just need to register a gateway and an application. This is straightforward and you only need to follow the instructions shown in the screen. I will start adding a new gateway. And here, the gateway ID configured in the packet forwarder should be entered as gateway EUI. But for this example, I will use a customized ID. After entering your gateway information, you just need to select the 2.4 GHz frequency plan. And once the packet forwarder is started on the gateway side, the status will be changed to connected to indicate that the communication succeeded. Now I will continue with the setup of our application for this demo. For this, we only need to add a new one with its name and description. Then we could add an end device to be activated by over-the-air. and after selecting the implemented LoRaWAN version, we should enter the corresponding activation keys and device UI. And do not forget to select the 2.4 GHz as frequency plan and the version of the regional parameters document which has been used. With this, the Things stack is ready for our demo. Finally, we just need to install the Arduino IDE to start programming our application for the end device. This is an easy-to-use open-source software. If it is the first time you work with our Arduino board, the first step is to add it to the board manager. For this, you should add the corresponding link to it. And then you should continue including the IMST library. You could download its latest version from our website. And finally, I have included the sensor drivers required for this demo. These are available under the Library Manager. Now it's everything ready, and I have already mounted my end device so that we can start with the implementation of the demo application. For this, we have prepared an example file and you only need to customize it. First of all, it's important to check that the configuration of the serial interface is the correct one for our Arduino board. Then, you should customize the keys for your own application. As said before, this demo will use the over-the-air activation to achieve the connection to the Things stack. And once our end device has been successfully activated, the sensor data, in this case the temperature and the humidity values, will be sent using the Cayenne format every 30 seconds to the Things stack. In the end, you should verify that the correct board and port are selected before going into the final step. And click Verify and Upload. On the other side, all exchange radio messages between our end device and the Things stack will be shown in the Live Data tab. By selecting the Cayenne format under Payload Formatter, the payload raw data will be interpreted and the sensor data will be shown in a human-readable format. As a final step, I have added an integration to Tago.io for the visualization of the sensor data. For this, you just need to add a webhook and enter your Tago.io authorization. Finally, you will be able to watch your live data using the serial monitor on the Arduino side, the complete radio message exchange on the Things stack, and the sensor data in Tago.io. To conclude with this demo, I could use the cold spray to modify the values of the temperature and the humidity of the sensor. And now we have to wait until the next uplink is sent, which will contain the updated data, and look if this worked. As you can see, the values were modified, and now you could also add some graphs for this visualization of the temperature and the humidity variations over the time. As the uplinks are sent every 30 seconds, now this part has been sped up to save some time during this session. But here you could see how the values of the temperature and humidity sensor will return slowly to their original values within the following radio messages. This is clearly visualized in the Tago.io dashboard. So that's all. We have come to the end of this demo and I hope you enjoyed it. If you still have some questions or you need further help, please contact us at IMST. We can offer you technical support in different areas, like antenna design, circuit design, and with any other topic within your wireless solution. We could also guide you through the whole certification process of your product. So, thank you very much for your attention, and don't forget to visit us at our IMST virtual booth. We will be there available if you need any further assistance, and we will answer all your questions. So bye, and looking forward to meeting you soon.